Assalamu alaikum and greetings. My name is Muhammad Azman bin Rosli. I work at Jerantut Community College under the Lifelong Learning Unit. My educational background is in the field of electrical and electronic engineering. Today, I would like to share a little bit about my presentation entitled Design and Simulation of Multi-Input Converter for Low-Power Hybrid Renewable Energy Sources. The background of the research: the energy inputs from a variety of renewable energy sources require an efficient power converter interface towards integrated management of power load. This paper looks into low-power hybrid renewable energy sources for multi-input converter design. The proposed MIC consists of a DC-DC boost converter and a single-phase full-bridge DC-AC inverter. The structure of MIC is simple compared to several single-input converters used for each source. The input sources applied in this work comprise photovoltaic, battery, and fuel cell. This MIC is capable of operating in 3 different operating modes, and power delivered to the load can be either individual or simultaneous. The first to third conditions occur when the power is delivered from either source individually. The fourth condition happens when power is demanded from 2 sources simultaneously. And finally, power is supplied by 3 sources simultaneously. The proposed converter was simulated using the National Instrument Multisim 12.0 circuit simulator, and the results are discussed in detail. The problem statement: by using the individual energy sources power system, additional energy sources are required to assist the main source in fulfilling the load demand. There is a lower reliability to deliver continuous power. Energy conversion efficiency is relatively low, cannot satisfy users' requirements for a stable power supply. And the second one, separate single input inverters is a complex configuration, high cost, and low integration. So the objective of the research is to design a multi-input converter topologies suitable for low-power hybrid renewable applications. Next, to develop a control strategy enabling seamless power flow among multiple sources. Then, to simulate and analyze system performance under various environmental and load conditions. The last objective is to validate the proposed MIC design through prototype modeling and comparison with existing methods. The research scope will concentrate on the simulation of new square wave topology for the multi-input inverter. The NI multisim circuit simulator is adopted in this work to observe the switching and circuit operating waveforms, where the switching related operation modes will be determined for the circuit. The experimentation work is also carried out to verify the simulation. In addition, the simulation study on different operation modes, effects on switching waveforms and loads are the extension of the work, which will be the preliminary results for further validation. Multi-input DC-DC converters combine multiple renewable energy sources that operate at different voltage levels. In this setup, all the sources are connected together to supply power to the load. The individual single input converters are employed for various sources as shown in figure here. Sources 1 through N may consist of such as photovoltaic system, battery, hydro fuel cells, microturbines, or the electrical grid. Source N represents the storage unit, which may include a battery, ultracapacitor, flywheel, or superconducting magnetic energy storage system. All renewable energy sources operate in one direction only, while the storage element can operate in both directions, allowing it to charge and discharge. A multi-input DC-DC converter has been designed to replace several parallel connected single converters, as shown like this figure. This converter facilitates the connection of various renewable energy sources to efficiently regulate the load voltage. The use of individual converters in renewable energy system typically results in increased architectural complexity, higher implementation costs, and limited flexibility for multi-source integration. To address these drawbacks, multi-input converters have been adopted as a more efficient and scalable interface for hybrid renewable energy system. This figure presents the block diagram of the proposed multi-input converter configuration. In this system, a maximum power point tracking controller based on the perturbation and observation algorithm is employed to ensure optimal energy extraction from the photovoltaic source. The proton exchange membrane fuel cells operates within its perceived optimal range to maintain steady-state performance, while a charge controller regulates the battery charging and discharging processes to enhance overall system reliability and continuity of supply. The electrical power delivered by the PV, photovoltaic, DG, battery, and FC fuel cell sources is coordinated through a multi-input DC-DC boost converter, where pulse width modulation is applied to regulate the DC bus voltage under varying input conditions. The conditioned DC output is subsequently processed by a DC-AC inverter utilizing sinus pulse width modulation to ensure balanced power transfer and high-quality AC output. So the inverter is designed to deliver a nominal output of 240 VAC, 50 Hz with a rate capacity of 300 watt, suitable for small-scale standalone or distributed renewable energy application. These are research questions. Question 1. What MIC topology is more suitable for integrating low-power hybrid renewable energy sources such as photovoltaic, battery, and fuel cells? Second, how can a mathematical model of the proposed MIC be formulated to analyze its steady-state and dynamic behavior? Third, what control strategy is required to ensure efficient multi-source integration with low ripple and improved dynamic performance? And the last one, how does the proposed MIC perform under various operating conditions compared to existing converters in terms of efficiency, stability, ripple, and transient? In order to satisfy the objective of the project, here are steps need to be implemented in order to ensure that all tasks are properly executed. The flowchart of the project is like this figure. Number 1, study on power converter, hybrid power system, and other materials. Study on the parameters of existing circuit. Second, circuit designing. Third, circuit simulation. Fourth, simulation result analysis. Fifth, hardware construction. Sixth, hardware testing or experimental. The last one is experimental result analysis. Regarding the control strategies, the proposed MIC is designed to accomplish two primary functions: output voltage regulation and facilitation of power generation from the three renewable energy input sources. Power width modulation is typically employed in the circuit to regulate the power switching device by generating pulse signals based on the duty cycle and switching frequency, thereby controlling its on and off states. During the turn-on interval, energy is stored in the capacitor. When the MOSFET switches off, the stored energy in the capacitor is transferred to the output of the power converter via the inverter input. This figure presents the control system block diagram for the MIC, comprising the 12-volt DC power supply, compensators, pulse width modulation, gate drive, and OR gate. The output signals from compensator 1 and 2 and 3 serve as input drive signals for PWM circuits 1, 2, and 3 respectively. Subsequently, the outputs of PWM circuits 1, 2, and 3 act as drive signals for GD circuits 1, 2, and 3. The gate drivers then control the switching device Q1, Q2, and Q3 accordingly. The pulse signals for Q1, Q2, and Q3 are regulated by adjusting the duty cycle and switching frequency within the PWM circuits. The control circuit is implemented in hardware utilizing an auxiliary analog circuit design. The DC output from the multi-input DC-DC boost converter is either regulated or inverted by a DC-AC inverter to generate a sinus current into the AC mains utilizing a sinus pulse with modulation controller. The block diagram of the control system for the voltage source DC AC inverter, like here, like this figure. The output voltage from the inverter is applied to the SPWM controller and monitored by the compensator as feedback control. The compensator's output serves as the input signal for the SPWM circuit, enabling adjustment of the reference voltage for the SPWM operation. The gate drive circuit's output signal control switch Q6 and Q7 to generate a sinus AC current. To ensure proper operation of the proposed DC AC inverter, the central control unit continuously monitors the output voltage. The control unit design is implemented using an auxiliary analog control circuit. Furthermore, the outputs of the GD circuits will independently drive the switching device QS. The outputs from all PWM circuits are combined to an OR gate circuit, which subsequently drive Q4. The pulse signal for Q1, Q2, and Q3 can be regulated by adjusting the duty cycle and switching frequency. This table presents the component values utilized during the simulation phase. I use a SG3524 IC to generate the PWM signal, of which we will create the square wave output. A general overview of the internal circuitry of this IC can be observed in this figure. The IC was the head of our inverter circuit and was heavily protected by fuses. The circuitry which utilized the SG3524 to create an output signal can be seen in this figure. Following the circuitry surrounding the SG3254 was the power amplification circuit. Here is a simple PWM DC to AC voltage inverter circuit based on IC SG3524. This IC chip is a fixed frequency PWM voltage regulator control circuit with indifferent outputs for single-ended or push-pull application. This IC integrated circuit has all the functions necessary for the production of a regulating power supply, electrical inverter or switching regulator on single chip. The operation modes of multi-input converter. For the operation mode 1, this is a circuit condition when the power source from V-in1 work individually. The second circuit of mode 1 when the power source from V-in2 work individually. And the third one when the power source from V-in3 work individually. So the second operation is mode 2. This is a circuit condition when the power source from V-in1 and V-in2 work simultaneously. The second operation, when the power source from V-in2 and V-in3 work simultaneously. And the third one, operation, when the power source from V-in1 and V-in3 work simultaneously. The third operation mode happens when all the sources V-in1, V-in2 and V-in3 work simultaneously. The system was designed and simulated using NI Multisim 12.0 software to verify the operating principle of the new multi-input converter. A 300-watt system was used as a benchmark. So this figure shows the waveform of the DC output current and voltage from the converter to the DC AC inverter using a single renewable energy source input. As example, it also displays the switching transistor that controls the load voltage and current. The generated DC power was measured at 300.2 watts. This figure presents the waveforms when two renewable energy sources are utilized, with the DC load power recorded at 367.7 watts. Finally, when the three renewable energy source input are engaged, as shown like this output result. The power output further to 319.2 watts. The regulated high power factor, AC, sine load current and voltage waveforms are displayed in this figure, which enhanced versions of this signal shown like this output. The inverter's output power was successfully regulated at 240 volt AC, achieving a maximum load power output of 300 watt. Through the application of a harmonic filter, the load consistently receives stable power irrespective of the number of active renewable energy sources. So the conclusion, in comparison with the previous topologies of hybridizing, the proposed converter can economize in the number of power components and simple structure is well suited for a hybrid power energy application for more than one input power sources. A successful outcome through design and development of efficient hybrid energy integration scheme would improve performance and usage of DC sources, especially in renewable energy, consequently improving electricity supply, efficiency and availability. The future enhancement of this work is to realize model or prototype of the multi-input converter for hybrid renewable energy power system. Thank you for watching.